Good morning. Thank you for joining our inaugural Open-NFP Summer Webinar Series. Nick Viljoen is going to present P4 for custom identification and flow tagging. This webinar will illustrate the use of P4 on an Agilio CX intelligent server adapter to enable identification and custom tagging for the rerouting of elastic traffic within a telecoms data center for virtualized compute nodes. Nick is a software engineer at Netronome, focusing on the enablement of real-time analytics at the compute node in the data plane using intelligent server adapters. He is currently collaborating with the Cord project at ON Lab to apply this within the context of the next-gen mobile edge network. Nick spent 4 years at the University of Cambridge, where he received his undergraduate degree and a master's in information engineering, focusing on causality and machine learning. And before I turn it over to Nick, I'll tell you a little bit about Open-NFP. Open-NFP's objective is to support and grow reusable applied research in data plane network functions processing. We do this by focusing on reducing the barriers to starting and performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4, the topic of this webinar. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems, as well as direct support from our engineers in a research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and webinars. We encourage proposals to research funding agencies. We invite you to join the 20+ universities and companies working directly with Open-NFP projects. And now I'll turn it over to Nick.
Hi, everyone. So I'm going to talk today about analytics, monitoring, and this idea of custom tagging and identification within the smartNIC. So just to run you through sort of the agenda for today. First up, we're just going to run through the objectives, what the aim is for people to understand by the end of the session today. After that, we're going to run through. I'm going to explain why do we want to put this analytics in the smartNIC? Why does it make sense to use the smartNIC, the NFP, as the place to enable this? And finally, we're going to focus on looking quickly at the trusted execution environment, which is a concept which we've developed with respect to how you can actually implement these kinds of sandbox functions, these things that we are working on, and these things we are trying to build on as sort of almost side projects isn't the right word, but how we can implement these within a larger data plane project, within things like OVS offload or vRouter offload, how we can use these together with the products we already have today, and really get things up and running quickly. It's kind of follows sort of a fail-fast model. And then we're going to run through the demo. I'll quickly step through the code. I'll explain sort of through block diagrams some of the ideas I have and how I want things to be structured. And then we'll quickly run a quick, simple sort of encap test just to show that the encapsulation happens. We look at the custom encapsulation, custom tagging we're doing. And then finally, we're going through to look at the de-encapsulation and then also monitoring and analytics on the flows. Finally, once we've done all this, I'm just going to quickly, if we have a little bit of time at the end, I'm going to run through this sort of smartNIC architecture, which includes the NFP and its sort of many core architecture and how it fits together. So you guys can have more of an understanding in terms of how to program the NFP and how to really make the stuff you build fly. And finally, we'll just summarize. So what is it I want you guys to run through today is, I want to understand, why the development of the next generation of data centers requires some of this compute node-based monitoring and the identification of potentially interesting traffic. That's where the sort of idea of what I call custom identification comes in. This is really about being able to see when particular flows are interesting. So this is, let's say we have particular types of traffic running, and we have particular flows which have suddenly start having a bit of jitter, or we have certain types of traffic which shouldn't be processing packets very often, but instead we have a lot of traffic coming through on those. So it's about looking for those kinds of use cases, then also understanding why the smartNIC, and then also how to interleave this with the data plane. We'll then also run through the programming options, so whether you use C, whether you use our P4-based sort of stateful P4 with a C plugin, or I'm also going to just mention eBPF, which is something we're looking at in the future, and I would encourage you guys as researchers to start having a look at. And then we'll run through the code. This is as I've explained it. So the first thing is, why is this important? Why is this disaggregation of the network something which means that this type of monitoring and this type of work based around the smartNIC becomes very important? The example I have here is on sort of the mobile edge network, because that's the stuff we've been working on, and this is some of the stuff we've been doing with some of our customers, some of our people we work with. At the Chord project I've been working on, this is something we've been looking at pretty closely. So the whole problem is that a lot of the monitoring in the previous generation of networks was based around boxes. So you have these sort of rack-based middle boxes where you had your MMEs, your S gateways, and your P gateways. These are all sort of items within your involved packet core. And the problem is these are getting totally virtualized now. So you get virtual machines whereby you have a virtual packet gateway, a virtual S gateway, and a VMME all sitting within a particular server. Now suddenly when you get to this environment, you're in a world where you can't monitor with boxes, you can't monitor with probing anymore, you can't monitor in a middle box environment effectively. And this is something I've seen, we've spoken to companies working on this, we've spoken to researchers working on this. This is a real problem people are running into now. And so the question is then, where can you do this? Now, a lot of people have been looking at this sort of concept of a virtual probe as effectively a virtual machine sitting within the server. The problem is, as soon as you start trying to flush a huge amount of traffic through those types of environments, you end up burning a huge amount of CPU. So this was really the high-level motivation for this work. This is where we were coming from. We were looking at this and we were trying to say, how can we fit in here? What can we do? And why is the NFP a great place to do this type of thing? As I've already run through, this is, why would you put this in the NFP? It's not feasible within CPU, and the spare computing cycles in the smartNIC, which is something we'll get to towards the end, allow us to be able to do this type of thing at low latency, because we're already collecting this data and we're already using this data for a lot of our virtual switching, for a lot of our data plane work. So if we can double it up and use it for analytics, that allows us to use far less cycles in terms of getting things from the memory and other issues such as that. So how does the monitoring work? There's sort of three stages. You have to have identification of potentially interstream traffic. And this involves sort of tagging higher-level control logic. So this is things like looking for particular port numbers, looking for particular types of traffic, and tagging those. So this is where something like P4 has a very strong capability, is in this sort of world of custom tagging, custom encapsulation. So you'll see we've kind of built up this vSlice header, which we use later, and we'll run through that in the code. And that's something which is very, very useful in terms of being able to do things totally flexibly. So if you look at some of the large sort of hyperscale data centers, those guys have really gone after building their own addressing schemes, building their own encapsulations. I know of some using MPLS tags to route traffic around the network. Others have taken IPv6 and split the IP fields into 64-bit fields. These are the types of things they're able to do, and this is the flexibility they have. What we're trying to do with the NFP is we can start providing this flexibility in other places. So this is where I think there's lots of interesting research topics to be had, is, because suddenly it opens up this large greenfield space which didn't exist before. because before you had to focus on, you had all these structures in place, you had all these protocols in place, and you had to fit to them, and there wasn't a lot of room for, should we call it, creativity. And suddenly we're allowed all these things to happen. All of this allows us to be able to look at things in a very different way to what we did before. So once we've done that, once we've used that sort of higher level control logic, we're able to focus particular flows into what I've called the trusted execution environment. This you'll see as a sort of P4C sandbox as well. This is something which fits within the NFP. So because of the structure of the NFP, you're able to partition it and use certain sections of the NFP to be able to do this type of thing. And that gives us a huge advantage. And this is why what we're trying to do is really, for the work you guys are doing, is to try and focus it towards things that might, can actually be used very quickly. Because if we are able to fit it into these structures, it becomes effectively mix and match, which allows code to basically go from an idea to production very quickly. So that gives you guys a lot of flexibility as academics to be able to propose things and to add things which can actually end up being used very, very quickly. And also with this deeper monitoring, obviously we can use the host stuff, but we're not going to focus on that today. And finally, this gives us the ability to react to potential problems because of the speed. We're able to see these things before they're noticeable to the end user. We'll run through an example of that in the code as well. I'm running through these very quickly because I really want to end up focusing on the code, and I want to focus on the kinds of issues you guys want to run into and the kind of things you might want to look at, and so that when you guys start playing with the code, when you guys start playing with P4, you know the kind of pitfalls and you know how to get around them. So this is just explaining the concept of the sandbox, which sits in the corner effectively as a trusted execution environment. If you're a carrier, this allows you to get a physical partition within the NFP, which is important when you don't have a lot of control over a lot of the other code. So it gives you the ability to flexibly and quickly adjust things and change things. And this is, again, where P4 comes into its own. P4, with this ability to enable flexible encapsulation, gives you the ability to very quickly prototype around the edges. Now, the key problem with the way P4 is structured, and it's because it is fundamentally a switching language, is that there's a certain lack of statefulness at times. And so this is what we, with our C plugins, actually are able to bring. And this is where we bring a huge thing which researchers aren't able to get to otherwise. So you've either got to build a very large amount of infrastructure in a language like C, or you need to be able to use something like eBPF, which is in some ways very strong and is probably in some ways better suited for these types of tasks. However, it takes a bit longer to get up and running. You've got a very strict verifier, which only allows certain type of code. And so P4 gives you this framework which you can very quickly get to the hub of your problem. You can very quickly focus on exactly the elements you want to focus on while testing things and while running through things. So that gives you a very strong environment to be able to quickly prototype things. And again, I've just got a few examples of what kind of things you want to look at with sort of predictive reaction, as I call it. Whitelisting, blacklisting, this would be if you see particular flows which are suspicious and want to block them. Compute node resource allocation, this would be if you saw particular VFs which were struggling, particular VFs which were not able to handle the amount of packets which are coming through them. So you can notice that through things like timestamping, which I'll show you later. That kind of thing would then give you a warning, and you can pass that up to the user who can then adjust. And obviously quality of service and service level agreements. If you see somebody using way too much data, then you should probably block them. So these are just very simple examples of actual real-world applications that this stuff could be applied to. And you can suddenly see running at speeds which you probably wouldn't have been able to show them at before. So this suddenly gives you a big greenfields area to go and often think of very creative ideas, think of very clever things which you wouldn't otherwise be able to do. And this is just to show an example of how, if you are doing this within OVS, you had your OVS running around the outside, and then we have our trusted execution environment, or P4C. sitting within the system, how we can then ensure that you can do very complex things here because you're not having to go through every single packet. That's all we're trying to show here, is the fact that using the system we've built, you can have very few packets heading towards complex analytics. So most packets, with your custom tagging schemes, with your monitoring, you're able to avoid them going towards anything where they have to do a lot of monitoring. You know, let's say we put regular expressions in. Let's say you guys wanted to do DPI on an NFP. You could send particular packets or particular flows to this environment to have this type of action happen to them. And it means that you're not holding up the entire pipeline. You're only looking at a very small group of packets. So you would write something like a simple, regular expression matcher within C, and then you can either have your P4 pipeline, you can have another pipeline around it, and then that can allow you to very, very quickly get up and running and show performance and speed which you wouldn't otherwise be able to do very quickly. And so this is also where the environment, the concept I'm talking about, comes into its own. It's this concept of having a transparent NFP. So the key problem that comes in is when you start building very custom code, which only works within the NFP environment, then it becomes very hard to translate it across different systems, get other researchers to engage with it, because you can only focus within the NFP-based environment. So that's where things like this P4C come into its own, because there's guys like a guy called John Fasterband at Intel, who you guys should all check out. He's done some great work. He's built a compiler which can translate the P4 into eBPF, and then that can then be pushed into an eBPF virtual machine within the kernel. So that suddenly you can have an NFP, you cannot have an NFP, and you can have all kinds of researchers being able to collaborate together very quickly and work on the same projects, and it makes the NFP totally transparent and just an environment which gives you something which is suddenly much faster and much more performant. The same thing if you want to code within eBPF, we have hooks which can then simply just pull things down from the x86 into the NFP. I would encourage you all guys to check out the NetDev mailing list, get involved with the Linux kernel. This is the work we're doing on there, and it'd be great to have academics piling in there and really getting involved. So without further ado, let's quickly run through the demo. So I'll quickly just show you guys kind of the conceptual setup we have, and then we'll go and we'll run through the code. We'll really look at what the sort of practical implications are of some of the things we do, and some of the pitfalls you will run into, because I've run into them all. But once we've done that, then we will show things actually working, and give you guys a few other tips as well in terms of how to prototype, which is something which actually I've spent a lot of time thinking about and a lot of time working on. So this is our sort of conceptual setup, and this is something which I demoed with Tom Tofig of AT&T at the P4 conference. And this is just a very simple 2 servers connected up. We slice the traffic, and then according to which particular slice it is, so we use a custom packet tag to indicate slice, which means you've only got a single tuple lookup on the other end to increase your speed, and then you're able to also monitor all the different ways, monitor the different types of traffic in different ways according to its slice. So this is the simple conceptual setup. In what I'm showing you guys today is I'm really going to be showing it in a way that you would run it if you were prototyping. So I haven't connected up 2 servers together, and I'm not running from the one with all the virtual machines running to the other, because the key thing is, and this is pitfall number 1, so big highlight here. If you are, because P4 is a compile time language rather than something which is more interpretive, it means that if we set up our VMs at the beginning, link them up, and then run our P4 program, we're going to have to tear them all down and pull them back up again if we are actually slightly changing the program or changing anything. Now that's a key problem because that really slows down development. So I'll show you guys how to push packets through virtual interfaces so that we look at how we can quickly prototype things on one server without having the whole setup running. And that gives you a lot more flexibility. Let's say you've only got one card. This gives you ways to just very quickly get up and running, test a much larger potential setup before you have to invest money in more cards, more servers, more of anything else. So let me just quickly run you through. So the way P4 works is with our system is we have our P4 programs, and this is a pretty in-depth slide just showing exactly the algorithm which I'm using. So you'll notice there's one dark block at the bottom right, and that's the only block which is using the C programs. So everything else is in P4. So this is the beauty of the way that we're using P4 and the way you guys can use P4 in your academic projects. P4 gives you a very quick way to build the whole system around it. And then the one piece of interest, apologies, I haven't got a mouse right now, but the one piece of interest, as you can see in the bottom right corner, gives you the ability to go and build much more complex, deep code within one particular block. So let me just quickly run you through this whole pipeline so you guys have an idea of what's going on. So we have our header definitions, which define what type of headers we have within our P4, what type of headers we're able to pass. Then as packets come in, we pass them and we go through our pass logic. We then, after we've gone through the pass logic and we've passed the packet as far as we can, we then pass it to control. First thing we do is, first thing with the pass is we look for the Ethernet header, hit the Ethernet header. We then look for what type of packet it is. If it's a virtual slice packet, VS, we would then go to that, pass that header, and then inside that we would have the normal IP, TCP, UDP headers. We then get pushed through to the control element. Control element would first check, okay, was there a vSlice header attached? So at this stage, if it's got through, we know it's an Ethernet packet. We look for the vSlice header. If there's a vSlice header, then we will apply control logic related to the vSlice header and send it to the decap table. If it's unknown and it's not a vSlice, but it's also not an IP packet, we will send it to a drop table because it's a security risk. We don't know what this type of packet is. For now, we'll just drop it. Later on, obviously, you can add far more complex logic. One thing you guys should look out for is we've got a couple of interns here for the summer who are building a big simple router in P4, which will give you a lot more complex functionality and will be a very useful thing for you guys to be able to use and just plug into just to get basic functionality running around the outside of your projects. On the other side, if you then have an IP packet, you then check if it's a TCP packet, you go to encapsulate it with the TCP table. If it's a UDP packet, you encapsulate it with the UDP table. And if it's unknown, you forward it on IP addresses. That then, all of these tables then feed into a set of actions we have, which are encapsulation, forward, drop, and our de-encapsulation / monitoring action. Now, the reason I have this set up this way and not pointing to particular actions is because different tables use different groups of actions. So you're not using a particular action for a particular table, you're using a particular group of actions, and you're matching on particular features within the packet, and that's then leading you to decide which one of those actions to use. And finally, it moves forward to the egress, and your packet goes on its merry way, hopefully. So what are we doing within this decap block? So we do the standard de-encapsulation, which is just popping off the vSlice headers. But then the other thing we also do is we do this monitoring. So let's have a quick look at our C action before we then go on to actually look at the code and look at it in anger. So the first thing we do is our header extraction. So this is just pulling off the vSlice header. So we can look at the vSlice, identify which one it is, and that match allows us to do the correct type of monitoring. The advantage of doing it this way is, again, you're only looking at a single tuple match. You're not having to look at something like a 5 tuple, or even at OVS, you can even have up to, I think, 17 tuple matching. This type of thing is a lot slower and a lot less performant. So this gives us a very simple way where we can totally flexibly define our own matches. If you want to match on 20 fields, you can do it on 20 fields. If you want to match on 1, you can do it on 1. The focus of our demo is we're going to run through the histogram monitoring, which is something which we developed at really at Chord. So this is something me and Tom demoed at P4 conference. And it gives us something very interesting to look at in terms of when you have certain sort of types of mission-critical IoT functions in the next generation of carrier networks. You need to be able to monitor these and ensure that these are running with the performance you need. Other systems you can monitor for things like service level agreement. You can monitor for things like security. You can monitor for things like anomalies. So, the examples we have here, and these are very straw man examples. Please don't, please don't say I'm encouraging this as a complete solution. We have voice packets. So usually voice packets tend to be fairly small. You're not getting, maximum transmission size packets. So we want to look at large packets there. If there are too many large packets, there might be an issue. So we might drop them. In non-critical IoT, these are things like if we end up with sort of lots of small connected sensors, these are sending a very small amount of traffic. We shouldn't be getting a huge amount of traffic from particular non-critical IoT functions. Now, what that leads to is us having a very simple way of monitoring the percentage of total traffic. And this is just using simple counters. This isn't using anything. I'm not trying to use anything too complicated here because I'm trying to have something very simple for you guys to then build on, you guys to use the code and go away and really add to what we have. And then using that, we can look at the percentage of total traffic, and then if there's too much of the total traffic, which is this non-critical IoT, we can drop it. And finally, if we see strange slices which you don't recognize, for now we just drop them. So, without further ado, let's go and run the demo. So, here we are. So this is the C code we have up and running. I'm going to quickly run you guys, just show you guys the code before we actually run anything. So as you see, I've already started the debugger here. So we have the debugger running. And within P4, we have header definitions. Here we are. So as you can see, it's as simple as defining any custom header. If we look at our vSlice header we've defined, we've given it an E-type, which we've defined up at the top. So we've given it its own E-type, ether type, and we have given it a slice number. So that's, at the moment, this is just an 8-bit number, so we just have literally a 24-bit small header here, which we've inserted. And it's totally custom, which this just shows the power of P4 to be able to do this type of thing. Now, then we have our header declaration, so we define all our headers. I've actually removed ARP from our project at the moment, which is why that's commented out. And then we get to our parsing stage. So as you can see, we start by passing the Ethernet. We start by running the Ethernet parse, which then looks at the E-types, looks at whether you have a vSlice, whether you have an IPv4 packet. This is what's explained within the diagram I just showed you guys. So here you can see that the real live code doing exactly the same thing as we've just shown you guys. We then define the actions. We define our match tables. And then finally we get to the control. The control here is really where the brains of the program is. This is where we're looking to see which types of tables we need to apply. And as you can see, we just got a very simple system here whereby we're looking for valid parsing of certain types of headers. And then, so without further ado, let's quickly run the decap example. So, sorry, the encap example. Let's run the encap example, and then once we're done with that, then we will look in more depth at the C file as well. So here we are. Let's focus on thread 0. So as you can see, it can take us to all kinds of different files. What you see here is a piece of assembler, which is not P4. Here we go. So as you can see, we've already started the debugger. So the debugger is ready. We're looking at a particular thread. We haven't pressed go yet, so we can't run anything on this yet. So we're going to just scroll down, and as you can see, we have line numbers here. So in the list file, which is what this all ends up compiling down to way down the line, we have a sort of command lines. We have lines of code, so we can see exactly where within our list file different actions sit. This is all done by the compiler. This is all automatic. And as you can see, we've added a couple of breakpoints here. So we've added a breakpoint here on the encapsulation now, which just shows whether our particular packet has matched on our encap packet. So if we go and look at our table, which shows what our rules are, so we're just going to send one UDP packet through. So all we're doing right now is we're just matching on the particular virtual function that packet comes from. So we'll just look at it, check it out, and send it across, and give it a tag. That's all we're going to do. Very, very simple for now. So if we go back here, and as you can see, the NFP has a huge amount of threads running at once. So what I'm actually looking at here is the different context threads, and I'm focusing on making sure I'm in the right one. So here we have our breakpoint. So hopefully, if all goes well, and this is now, I'm now throwing myself into the hands of the demo gods. We have this particular breakpoint here, and we should hit that breakpoint if we are successfully encapsulating a packet. So let's see what happens. So here we are logged into the server. I'm going to have 2 logins. So we're here in root, so we're just looking to send a packet across. So we're just sending one packet of UDP traffic. And let's see what happens. So before we do that, we need to run this. So we get this running. So packet should now be able to run through. And let's see. Now there is a possibility, and this is something you guys are going to run into. You guys are going to set breakpoints like this in threads, and then a different thread may actually be being used. So as soon as you set this breakpoint, you run your packets through, and something's gone wrong. Why am I not hitting my breakpoint? A key thing is you've got to understand that the NFP could be using any one of a huge number of threads. So to be able to really do it, you've got to go across the threads, set breakpoints in each one, but it's highly likely that you're going to be using, for the first couple of packets, you're going to be using the PIF app NFD master.list. So you're going to be using microengine 32.0. So that microengine is the highly likely one to be the one where the first packet's going to go. So if you set your breakpoints in there, you're probably going to be successful in hitting things. So that's a key point when you guys are busy programming this, to use that and ensure that you focus on that. So the other, it's also more likely that it's going to be thread 2, 4, and 6 in here rather than anything else. So these are really, if you're going to set breakpoints anywhere, set them in these 4 first. And if that isn't enough, then you can look at going to other places. So let's see what happens. Yep, there we go. Successful. So as you can see, we've hit our breakpoint, so we've successfully matched on that packet, and now we will be encapsulating it with a vSlice tag and forwarding it on. So let's have a look at the header. So this is before the vSlice is added, so it's not there yet, but you can see we've got our Ethernet header, IPv4 packet, and then we've got our IPv4 header. As you can see, the fields in here are the fields I've defined in here. So you can see these are the fields, same fields. So everything comes back to what you've defined. This is not being done by some third-party process. This is being done by exactly how you've defined it at the top of your P4 file. So I think without further ado, let's send that packet on its way. Oh, so last thing here. So you'll be like, oh, wait, hang on. We've got stop and go at the same time. What's going on here? So all we've stopped is this particular thread. The rest of the NFP is still running. this is something, it's important to understand this. When you've got this concept of this multi-threaded system, you need to be thinking slightly differently when you debug it. Now, if you need to work out which threads are running, there is a really useful window in here called thread status. This gives you the line number which each one of the threads is currently on. Now, using that gives you the ability to be able to identify which threads are still, so you can see most of these are right at the top, so they're not really running at the moment. They haven't got any packets running through them. The only one is microengine 32.0, where on a particular thread, so in this case actually thread 4, as you can see, so we're on thread 4 here, has got this packet. So that's why it's key having these on, on the first, having all the breakpoints on the first microengine, because PIF app NFD master is going to be the one which most likely hits the packets when you're doing debug. So you can see the first couple, so this is because we're using a shared code store. The first couple of microengines are on PIF app NFD master. However, the other microengines are on PIF app NFD. So that's a key little tip. Ensure you remember that whenever you're doing anything on the system. So let's send that packet on its merry way. Okay, so we're going to get rid of this now. And now we're going to look at the de-encapsulation and monitoring side. So again, we have a very simple P4 pipeline. All we're doing is we're going to match on, we're going to have a valid vSlice in our packets, so we're going to apply the decap table. We go to the decap table, we're going to just match on the vSlice, and we're going to run the decap action. Now, as you can see, when we get to the decap action is running other actions as well. So we're modifying fields, we're removing headers, but we're also running the filter func. Now, the filter func in this case, this is our primitive action. So this is our C action right here. This is where the magic happens, this one here. So what we will do is we will use that one to be able to run much more custom functionality. So we'll run through that in a second. So let's have a look what happens once we go in there. So here is our C function. Now you'll see things like I'm doing all this stuff about defining particular variables as shared. This is key when you're working across the NFP because you're so multi-threaded. If you want to have global variables, things you're measuring on a global level, the first tip is it's better to have things which are read-write, so you can write things up. So things like histograms work well, counters, these types of things, not things where you're read-write, 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 unless they don't have to be very precise. So that's why when I'm doing things which I'll run through in a second, such as looking at the amount of packets in a certain number which are going through a particular type of slice, that kind of thing is fine because you're not looking to be, it's not an exact number you want. You just want to be in the vicinity of a number. So these are the types of things you need to bear in mind. And these shared volatile memories are things which we can ensure that they stay in shared memory. They don't get optimized by the compiler. That's what the volatile is about. It's about ensuring it stays there. So the first thing we're doing is our header extraction. So using the PIF plugin, so this is again, so you can see here, we've defined a vSlice type. So that means that this intrinsically exists, this definition here. So this is something which comes about with our P4, so we've got all these custom interfaces through to our C functions, which means a lot of the work you would otherwise have to do in the C function is already done by using your simple P4 definitions. Then we have our PIF plugin for the IPv4. This is again just the same thing, and then we quickly extract our headers so we can have a look at them. So here we start our slice matching. So for slice 0, so here we go. Look for slice 0. We will from there be able to look into there and look at all the different variables we have within there. So you'll see I've defined things here, and I will go through this in a second. I'll run through the microengine itself. The GPRs here, so I've done some definition of in terms of exactly which memory within the transactional memory system I want things. And actually I've defined these as being within registers. Now you'll see there's a reason for that in a second. And then we just run through our code. We've got our simple histograms. You'll see at the moment I'm doing something which I'm not particularly proud of here, which is actually going through each particular bucket within the histogram and seeing whether there's a match within that particular bucket. So doing that allows us to just have something very simple, which is very easy to read. I will probably upstream it like this so you guys can see it. However, this is not the correct way to do things if you're looking to be as efficient as possible in terms of cycles. I had a masking scheme which I was using, but it's slightly more confusing and slightly less clear what's going on. So this gives you the ability to be very clear. And then finally we have the other slices as well, where we're just doing some very simple counters effectively, just to check that we're not seeing too many of the large packets, or that we're seeing too many of a particular type of packets in a group. Now this is key. This is where our state comes in. This is where the power of state sits. Being able to look at things like a histogram, have an entire histogram stored, allows us to be able to really use state in a way that gives a lot of power in the compute node. Now we share the P4 language with switches, and I think the way it's designed at the moment, it works very well for switches as is. And that's great. And I think the guys here, people like Bappy, people like Johan, who've been really working on the P4 stuff, have done a great job, as well as the guys from Barefoot and the guys from everybody else who are involved. But at the NIC, we have slightly different needs. Sometimes we need a bit more statefulness, and that's where this stuff comes in. Now, the next thing I want to run through, just quickly before we run through the code, is the mailboxes here. So something you'll see once we start running the program is that some of the variables are optimized away. So you'll try and set data watches. So let's try and set a data watch for a particular variable. Let's see what happens if we try and do this. Nope, it's not going to let me do that across from my Mac. So sorry, I'm RDPing across here, so I'm afraid I can't do that. But what happens is you're going to see a message down here at the bottom saying a variable is optimized away. Now that's because the compiler has pushed that into a register. Now when you push something into a register, that means that you're in the position whereby you can't see it as a data watch. So if we set a data watch on that particular variable, you couldn't see it. Now that's where the mailboxes come in. So the mailboxes are the fail-safe way to be able to effectively do what you would normally do in a standard C program as a printf. So that gives you a way to do that and to run through that very quickly and to be able to check that the values you're seeing are the values you expect. So as you can see, we've got all three of our mailboxes here, and we will have packets running through those. And then we also have our IoT histogram, which we're monitoring. Now, without further ado, let's get some packets running. So we need to quickly and then in here we should have yep, we have our vslice long. So this is just a simple 1,000 packet PCAP with load of packets from vslice 0. Now, if I can find where I've last pulled that command. Yep, there we go. So we'll run through this, and let's have a look what happens. So right now, we don't see anything. Let's refresh this. And look, we get this error. So we couldn't perform a particular read while the MEs are running. So you'll see this happens for every single one of our elements here. Now at this point you're thinking, oh no, something's gone really badly wrong. But what this is actually doing is because we're running live and because these are variables where things are being written to, we can't monitor it live. So what do we have to do? How are we going to do this? We're going to quickly stop debugging there. And there we go. Now we get our values. So you can see we've had a bunch of packets which take forever. So I kind of set it up like this, and I've kind of set my mask like this. We've had a lot of packets which have taken a very long time, and some which were very quick. So you can see that here. So we can go to the mailboxes, and we can monitor when the previous packet arrived, when the current time delta packet arrived, and we can look at the number which is the time delta. So here's the time delta, and here are the numbers for in terms of when the packet came and when the previous packet came. And that difference here gives us this number. You guys can go off and check this if you guys want to check me up. But this gives us a huge amount of power. At the moment, I'm just using a very simple 32-bit timestamp, which wraps pretty quickly. But there's actually a 40-bit timestamp within the NFP, which wraps, I think, every couple of years. So that shouldn't be too much of a danger. So this gives us a huge amount of power in being able to really monitor things live as we're running them. So if we run it again, then we can just go again. Simple. And then we stop it, and the values have changed again. And as you can see, this time the packets have gone at a slightly different rate. So this gives us a lot of power. Now, the last thing I quickly want to run through is how you can start doing things like control and drop in here. And this will be very, very quick. So here we have slice 2. So if we just quickly run to the particular thread, we go back in here, we have our slice 2, and if we see out of 1,000 packets, if we see more than 1,000 packets of what we're calling here non-critical IoT, then we're going to start dropping them. So this is for if somebody, let's say we had and obviously this is a very straw man. Let's say we had somebody who compromised sort of an IoT node and just started firing packets to some sort of denial of service attack. So let's just quickly run through that example, and then we will be done. Let me just quickly find it. There we go. So we're running through 1,001 of these packets. So if there's just 1,000 of them, we should be okay. But if there's 1,001, we should be hitting that drop. So let's see what happens. Now, as I said before, we may have something happen out of line here. I'm taking this to the edge by running it at a 1,001. So we may miss this one, but let's see what happens. Yep, we've hit it. There we go. So in our very, very straw man universe, we've stopped that denial of service attack. And that's it, really, on the code side. So if we head back to the C code, and then, so this is just the last thing I quickly want to run you through. This is the micro engine. So when you're looking at things like the general purpose registers, there what's sitting up here is termed as A and B. And we have this hierarchical memory structure on the back of it. Now, what you'll notice with the micro engine is there's a huge amount of memory on the actual micro engine as a very small processor. So that means you've got a huge amount of registers, you've got a lot of flexibility. So when you're working in the C, you can really actually squeeze a huge amount of performance out of this. So suddenly you have the best of both worlds. You have this P4 world around you, whereby you can very quickly focus on what you want to focus on, and then once you're focused on in there, you can really squeeze a huge amount of performance out of this. So that's really all I want to leave you guys with. That, combined with a highly multi-threaded, so each one of these have 8 time multiplex threads. That highly multi-threaded nature, combined with the many cores, combined with the ME itself, gives us a huge amount of power to be able to run the types of programs I've just described. So these are just some definitions. I'll run through these at some other point. The key thing is just that we end up with about 20 times as many cycles available with this NFP architecture, which gives you guys a huge amount of power to go out and innovate. I'm going to check. I presume we have some questions, Bapi. So let's stop it there and dive into questions. So the first question we have is, what is the timestamp delta and how do you compute it? So if we go across to the code and we look at, and this will all be available for you guys to look through in detail. If we go here, what we're doing is we are saving the timestamps to the lower 32 bits of the timestamp. We're saving in a register, timestamp low, and we're reading the low timestamp. So this is something this is a primitive which we're grabbing from within the NFP. This stuff exists, and you can find in the documentation, you can find more details about where they are and what they do. Or you can actually just go and, if you have the Programmer Studio, once you have it, you can go and dive through the code and find all these primitives. They're all sitting there, and you can access all of them from your C sandbox. And then we have, so in the first packet, we store the timestamp below is the previous timestamp. That's what we're using here, previous timestamp. So sorry, there's been a slight mess with the variable name here, so I apologize for that. But the timestamp delta then just becomes the previous timestamp, so the current timestamp minus the previous timestamp. So it's just the delta between the previous packet and this packet in terms of timing. That's all it is. Very simple, and this is something which is very powerful for detecting faults, for isolating use cases, and for isolating problems. So that's what it is. So the next question is, how do we develop a higher level abstraction UI for users to monitor various slice behaviors? And are there any resources for anomaly detection / the monitoring use case? So this is the thing I'm quite interested in. So I will. So there's a couple of presentations I've done which are very high level with Tom Tofig from AT&T, which you guys are welcome to check out. This was at ONS. We also did something at the P4 workshop, and then I also had a chat at the Open-NFP summit. So you can go and check those out on a very high level, and on a slightly more detailed level, I'm willing to talk to anyone about more, precise anomaly detection use cases, more precise mappings, that kind of thing. I'm very happy to talk about that at depth. My email is at the back of these slides, which you guys will be able to see. So if you guys have any use cases, we're very much looking for them as well. So come and join up and let's have a chat. In more detail, I've done some work on using machine learning algorithms within this. So there's also some potential there. So the next question is the concept I've mentioned, which is the TE, Trusted Execution Environment. What does that mean? I called it a C sandbox, but let's go into more detail. So what I mean by this concept is the fact that we have this space where we can go and we can, whether you're a carrier or a data center provider, so data center guys tend to have a bit more flexibility because they really control the whole network. Whereas this is very much a use case within carriers whereby they need to have their own space where they can innovate and they can suddenly start doing their own things because there's all kinds of VNFs, there's all kinds of other people within their network. And so if they start innovating in a non-isolated world, it means that they could run into significant problems with other VNFs. So what this allows them to do is this gives them an isolated space where they can go. It's effectively it's almost like you can almost think of it as a VM inside a NFP. It's almost the way you can think about it. So it gives you your own little space with your own piece of memory where you can do your own pieces of code and you can trust what happens there and you know that nobody else is able to read or write there. So that's what it gives you. That's the power, and it's really a concept which we developed as the C sandbox. The name Trusted Execution Environment is really only just to illustrate the fact that you've got this slightly small space where as a data center provider or as a carrier, you can innovate without having to worry about what other people are doing. The next question is, instead of declaring an array of memory in C sandbox, could we use register as a P4 primitive? Do they have any semantics in terms of memory location and concurrency? So I assume by concurrency you mean concurrency within P4 and memory location in terms of how you can define memory locations within P4. As far as I'm aware, and there are probably some people who know more about this on the call than I do. That kind of very precise memory allocation is not something which is currently available in P4. So if we look at the stuff you can kind of get in P4, there's lots of counters. We've got some counters here which we add as the NFP as well. And you can add watches, and there are definitely some structures within P4 which can allow you to do some of this work, especially the counters. So some of the simple stuff I've implemented here, like the counters, you could probably do that in P4, in pure P4. So you could run that and get that running pretty quickly. I've done it this way just to illustrate the use case, and we can do far more complex things and store far more data. So if you were trying to like store random counters in P4, some of that might be challenging. That's because it's a language we're sharing with others, and we have to make sure that we keep it open, and we keep it so that everyone's hardware can run on it, everyone's systems can use it, so that it becomes language independent. Sorry, it becomes hardware independent. And that's the key thing I think we're all striving for at the moment, is hardware independence, so that we're totally transparent. And you guys can run your stuff on our machine. You can run it on an x86, or you could run it on, if it's just a P4 program, something like a switch. So that's why we're using a lot of, and things like this histogram primitive, this would be very hard, I think, to do within just pure P4. But if you want to do more complicated stuff, you definitely need to be within the C sandbox, especially if it becomes more stateful. So let me just quickly try one last question here. So if I add a tag, a flow ID, into metadata in the data path for each packet designated to the host app, then can the host app use this flow ID? Suppose the host app uses DPDK PMD to get the packets. Do we need to change DPDK PMD in order to pass the flow ID and metadata into the host app? Okay, so it depends how we do things. So as I understand it, DPDK is able to handle, because what you're doing with DPDK is you're fundamentally just allocating physical addressing space and moving packets around like that. So I don't think, and this is something I would have to go and think about, I can't give you a perfect answer right now, but I can't foresee any problem, because fundamentally what DPDK is looking at is DPDK is looking at the DPDK is just grabbing pieces of memory. As long as the VNF or the virtual machine or the application which is running on the host could use the slice, or could understand the encapsulation, then it should be fine. DPDK, I don't believe, should have an issue with this. But I'm more than happy to talk about that offline and dive into more depth. So I think we're pretty much done there, guys. I'd like to thank you all for listening. Thank you, everybody who's here. If you have any more questions, I will just quickly dive back to the slide and say, here's my email address, and just get in contact. I'd love to have a chat with anyone and everyone. So thank you, guys. Thanks for your attendance. I really appreciate it. I hope you guys check out the rest of the summer series. We've got another one next week, I believe. And that will be, in 2 weeks' time. So please come, check it out, and let's keep the discussions going. Oh, and guys, go onto the Open-NFP website and join the mailing list. The mailing list is active. We're answering questions on there. There's a lot of discussion, a lot of development. Join that. Get on the Linux mailing list. Start playing with eBPF. Do everything. Yep. Do it all. Thanks, guys. Thank you very much for
attending. Thank you, Nick. Thank you very much for participating, everybody. Please visit open-nfp.org for more information, and we will also be sending out the link to the webinar and slides in the next day. And please join us, like Nick said, in 2 weeks for our next webinar. Thanks again.